Okay, and let's, just for the sake of the video, we're doing the upper hemisphere, and we're going to do a surface integral over the upper hemisphere. We don't have to know what we're doing the surface integral of. We're doing the surface integral of whatever we're doing the surface integral of, but it's going to be a surface integral over the surface comprised by the upper hemisphere of this sphere, which we know is a sphere of radius 4 centered at the origin. We partition this by first, now there are a couple of ways to do it. We're going to partition it this way, and then we're going to partition it using spherical coordinates just so we can see the connections. So our partition starts with our parameterization starts with parameterizing circles about the origin, centered at the origin, in the UV and the XY plane. So these circles, standard parameterization for a circle, and this would be a circle of radius u. Okay, so we have circles of radius u, and these circles can be thought of as starting in the XY plane, starting from the origin and spreading out until they get to the boundaries of the hemisphere. Now, the hemisphere has radius 4, so the circles will go out to radius 4, so that this is now, with these limits on u and v going from 0 to 2 pi naturally, so we do the whole circle, and u going from 0 to 4, so the circles spread out from the origin like ripples on a pond to the boundary of the sphere. And I forget what the context of or the syntax of my sentence has been, but we get these circles, and we now have a parameterization of a circle in the XY plane of the interior of a circle on the XY plane, or the interior of the boundary. Now, above every point in the XY plane, we've got a point on that sphere. So the point on the sphere is located, well, let's look at this. Okay, again, we have a z-axis here. Here's our XY plane. Okay, here's the point XY. It's a distance u from the origin, and we're looking at the XY plane from the plane, so we don't see the x and the y axes. But in any case, this point will be at distance u from the origin. And now we have this little triangle that allows us to determine how far we've got to go up to get z. And here's the triangle, u here, 4 here, square root of 16 minus u squared here. So that now z is the square root of 16 minus u squared, and now we have a parameterization. In parameter space, in u versus v parameter space, this parameterization gives us a rectangle. We partition the rectangle, partition the v's to get vertical strips, partition the u's to get horizontal strips, and that gives us a set of rectangles. If this is the ij region of the partition, that region maps onto the sphere, the hemisphere. Now I'll go ahead and do a three-dimensional, an attempt at a three-dimensional picture of the sphere. It's not very good. That's kind of squared off there. But we're going to have this, and we're going to have this, and then we're going to have something kind of looks like this. It's got to be a little more rounded back here. So that's a very crude representation of the hemisphere. This region, by this breakdown of the partition, is going to be some region, is going to map, we think of mapping, to some region on the sphere. So this maps here. Okay, now we can think of the mapping as being defined by an R vector, and your text likes to use bracket notation. I like to use IJK notation because it's less confusing, but I don't think anybody would be confused at this point. But R is going to be, of course, xi plus yj plus zk, but then x is u cosine v, and y is u sine v, and then we have our square root of 16 minus u squared z, well, our zk, 6 squared 16 minus u squared k. Okay, well, if this is a tiny region, these little arcs that form the boundaries of the region to which this rectangle maps are very approximately straight lines, and if this is small, they make a parallelogram. Okay, so this is going to be a parallelogram. And when I drew it, I kind of made it look almost rectangular. It's going to be a parallelogram. The length of this side is going to be related to the length of, well, let's just say it's related to the length of this side. I'm not going to worry about which side goes where at the moment. But yeah, this side represents a change in your angle V, and as your angle V changes, you're going to move in this direction. So that's just about right. Okay, so we have this side. Now, what's the length of this side? The length of this side is your delta V up here. So let's let me just draw a bigger picture of this rectangle. So this side is a delta V, and of course we can have this side is going to be a delta U. If we have a delta V, I wish I'd have left myself more room here, but if we have a delta V here, that's going to drive R into a change. Okay, and what's the change in R going to be? Okay, I'm going to have to come over here. I'm going to redraw that. We got delta U and delta V. Okay. Delta U in your parameter space maps to delta R in three-dimensional space, where delta R is approximately partial of R with respect to U times delta U. This will be a vector, and this vector is going to be this side. So that on our surface, here is partial of R with respect to U, delta U. And similarly, then our delta V is going to drive a change in V. The change in V And actually, I kind of got these backwards. This should have really been here, but for the sake of understanding what's going on, yeah, just kind of rotate the figure. We're going to have also here partial of V, partial of R. I don't know how I'm going to repair that. Partial of R with respect to V, delta V, and that's going to be this vector. Well, this is a vector we're going to call TU. It's tangent to the surface, or approximately tangent to the surface. Now, these are all approximations. This is an approximation. This is an approximation. Okay, so we'll just say this. This is an approximation. This is an approximation. But as we shrink our partition, the intervals in our partition, the little squares in our partition of the rectangle in parameter space, it doesn't matter where you calculate this delta V with respect to U. You can calculate it at a sample point, as we usually do. It's going to be very close to this vector, and at the sample point you calculate this, it's going to be very close to this vector. So I'm going to refer to a sample point V star or U star to indicate the implicit sum that we get when we do the double sum on this partition, on this parameter region. Okay. Now the big point is that the area which I'll just call delta A star, the area, and I can even, now the V and the U, the V star and U star could have been subscripted with I's and J's and so forth, but you want to think through how that would be. It's all implicit here. The area delta A star sub ij, if you wish, if this is the ij partition, then is just the cross product, the magnitude of the cross product of these two vectors. Because this region is now an approximate rectangle, parallelogram, sorry. It's an approximate parallelogram and if I redraw the parallelogram just for, it's the parallelogram formed by these, well, it shouldn't have an arrow on it, by these two vectors. Okay, this is a region approximate region, delta Aij star is approximated by these two vectors, and what's the area of a parallelogram? This is a parallelogram. Of course, we've got to be aware, and we should be completely aware at this point, that the area of a parallelogram is just the cross product, and we have to understand why. You know, this side has magnitude Tu, this side has magnitude TV. There's some angle between these two. so that the altitude of this parallelogram would be the magnitude of TV times the sine of this angle. And of course, the magnitude of this is the magnitude of TU times magnitude of TV times the sine of the angle. So that's something, that and the triple cross product, actually just have to be part of your mental makeup at this point. So if it's not, you should review it. But anyhow, by this well-established fact, this is the area of this thing. So the surface area, which I'll call S, then becomes the double integral over the region D. Okay, so let's call this region D in UV space of magnitude of TU cross TV. And of course the limits here are just U goes from 0 to 4 and D goes from 0 to 2 pi. So that'll be a very simple integral. Okay, well that's a surface area. Once you have the parameterization, it's very easy to calculate your dr du. What's your dr du? It's cosine v times I plus sine v times j plus what? 2u, right? And it'd be a negative 2u over the square root of, well, negative 1/2 of 2u. So it's going to be negative u over the square root of 16 minus u squared. Straightforward derivative. The TV, an even more straightforward derivative. You're just going to get a negative u sine v times I and a u cosine v times j. So that calculating this cross product is just going to be a simple exercise. Now, somebody should have screamed because a lot of this is off the screen. But you can refer to the video. So the whole idea, the whole concept is to have parameterization with constant, in this case at least, with constant limits on u and v, giving us, in this case, a rectangle in parameter space that maps to the surface of the sphere, giving us this approximate rectangle dimensions, this approximate parallelogram with dimensions tu by tv, and an angle that allows us to calculate this area by the cross product of tu with tv. Okay, well, the problem then asks you to find something else. And let me look back at the problem. You're trying to integrate x squared plus y squared times z. Okay? So now, the integral over the surface of, and I'm using S here, we'll just say hemisphere. This is going to become the double integral of x squared plus y squared, which is u, times z, which is the square root of 16 minus u squared, times magnitude of tu cross tv, and it's going to be du dv. And u is going to go from 0 to 2 pi. V is going to go from 0 to 4. So all we've got to do is calculate tu cross TV. Well, TU, and according to my notation, is partial of R with respect to U. And I invoke the R vector because it's a vector that we understand. Okay? And that is, sorry, Richard, you made a noise?
Question.
Yeah.
Yeah, I think, so you have x squared plus y squared times quantity times z is u times the square root of 16 minus u squared. Would that not be u squared times the square root of 16 minus u?
Yeah, good eye. Okay? You knew I was going to screw something up, so I'm glad you were watching. Okay, very good. Yeah, I wanted you there because it'd make this easy to integrate, but that's not relevant because this is going to have stuff in it too. So I just wrote it down carelessly. Okay, anyhow, your TU is this partial derivative, which is going to be negative sine V I plus cosine Vj minus u over the square root of 16 minus u squared. Okay. And this is actually kind of convenient because you have that 16 square root of 16 minus u squared in the denominator, which is going to divide into this and disappear. Okay. TV is a partial of R with respect to V. Okay. Oh no, whoa. I just calculated TV up here and called it TU. So this is TV, partial of U with respect to V, except I mixed things up, so let me write it down again and write it correctly because I was taking the derivative with respect to V and then I switched to take the derivative with respect to U. Yeah, I guess probably easiest just to change this. And this is not even a function of, the K component's not even a function of V, so its derivative is 0. Okay, I think I did that right now. And now the partial with respect to U, see if I can round that V off to make it look like a U, that worked. Okay, we're going to have cosine V times your I vector plus sine V times your J vector. And then that's going to be minus U over the square root of 16 minus U squared times your K vector. I really wanted to see that, so I went ahead and just did it. But yeah, I don't need excuses. Okay, I just messed it up. Well, we can do the cross product. There's enough stuff here. I like to do cross products by distributive law, which is fairly easy. You do sine Vi cross with sine Vj, you're going to get a sine squared V times negative I cross J, which is going to be negative K, and the cosine is going to match up with this, and then this is going to match up with this. This is going to match up with this. It's a little hard to look at it. So we can just write down the I, J, K, partial with respect to U, partial with respect to V. I don't know why we're doing that. I'm not doing a gradient. Didn't leave myself enough room. So it's going to be kind of small. Well, there it is. And what you're going to have then is you're going to have I times I'm not going to have room to write it here, so let me get this other board. And I probably have to pull this one over a little bit. Don't have a lot of room here. Okay, so TU cross TV is then going to be negative u sine v over the square root of 16 minus u squared times I. And again, I'm just looking at this determinant here. I probably can't see that on the camera out there, but probably a little hard to see from there because it's pretty far away from the computer. But we see what we do here, okay? And then it's going to be j times, and that should be a cosine of v here. And that's going to be then plus j I'm going to have this, and then k is going to be times negative sine squared v plus cosine squared v. Now there's the k, okay. So this is equal to see if I want to simplify that before I write it out. Yeah, we'll do it. U over the square root of 16 minus u squared times cosine vi plus sine v j plus k. So the magnitude of TU cross TV, and the arrow goes over the T, not the U, is going to be the square root of, well, this vector has magnitude U over 16 minus U squared. If you work it out, you're going to find that when you square the magnitude of this part, you're going to get U squared over 16 minus U squared plus 1. Which leads us to the integral now of U squared times 16 minus U squared times the square root of 1 plus U squared over 16 minus U squared du dv. And then you go to your standard integration technique. And I don't want to go into all that detail. Your 16 minus U squared and this is the square root of 16 minus u squared. You take this under the square root here, which will give you, okay, this becomes u squared times the square root of 16 minus u squared plus u squared, which is very convenient because now you end up just integrating 4u squared. And that's not going to come out with the same answer as your book gives you, because you're going to end up integrating u squared, giving you u cubed over 2. Did I do something wrong here?
What about that negative sine squared b on top?
The what now?
What about that negative sine squared b?
That does throw a fly in the ointment. Let's see. That's from the k. It's going to have negative sine squared b. I was just careless. It's this minus the cosine squared.
Okay.
If you do if you do the determinant correctly, that's what you get. My problem here is you're going to get a factor of 3 in the denominator, and you're not going to get any 3's out of these limits on the integral when you cube them, whatever. You're going to get 64 and 8, which is going to give you 1,024, but you got a 3 in the denominator, which is totally ignorant. If that was just a u, I think you might end up with the right result. No, you wouldn't be big enough. So there's something wrong here. I'm not going to worry about it. It's just not worth belaboring. See if there's an error somewhere here. There are a lot of steps. And go ahead and see how the integral works out. Again, I'm getting a factor of 3 in the denominator. Everything else that you get is going to be a power of 2. And the powers of 2 are relatively prime to 3. And the answer is 512 pi. I'm getting 1,024 pi over 3. That 1,024 is not divisible by 3. It certainly doesn't give you 512. It gives me something between Richard's answer to this question, which was 256 pi, and the book's answer, which I believe is almost certainly true, 512 pi. So there's some arithmetic error in here, but that's how the thing is set up. Okay, now briefly,